All right, everyone, welcome back. So, moving on in our solutions and solubility unit, we are going to look at the first part of chapter 8.2 today, and we're going to look at the solubility in water. So, what are we talking about today? We're going to talk about forces between particles in solution. We are going to talk about solubility in water, and we are going to talk about predicting solubility, which I know we did already in an earlier unit. So, that's going to be a little bit more of a review. So some learning goals for today's lesson. We are going to identify the three categories of forces between particles. We are going to describe the solubility of ionic, molecular, and polar solvents in water. We are going to predict the solubility of ionic compounds using ion charge and ion size. And we are going to predict the solubility of ionic compounds using the solubility guidelines. So let's jump in. First, we have solubility and those forces between particles. So, the formation of most solutions depends on the relative strength of three categories. The first one is the forces that attract the particles of the solute to each other, and we like to call those solute-solute interactions. The second would be the forces that attract the particles of the solute to the particles of the solvent. So that would be our solute to solvent interactions. And lastly, which I'm sure you can guess, are the forces that attract particles of the solvent to each other, which would be our solvent-solvent interactions. So in our lesson before, we talked about how solutions have two main components, the solute and the solvent. And it makes sense that if those are the two components, that there's going to be forces interacting that are going to affect the solubility of a compound. So we have those solute-solute interactions, the solute-solvent interactions, and the solvent-solvent interactions. So let's talk about solubility in water. So water is a very good solvent. Its polar nature of the water molecules enables the water to dissolve a wide range of solutes. So we know that water is a polar molecule, and that's the reason that it's such a good solvent. The oxygen atoms have a small net negative charge, and that leaves the hydrogen atoms with a net positive charge. And if we look at the picture that I have up here by the solubility, let me get my little laser. Over here, if we see, right, this oxygen, the red oxygen, has the net negative charge, and our two hydrogens are left with a positive charge. So the attraction between the hydrogen atom on one molecule and a very electronegative atom on another molecule results in something called hydrogen bonding. So if we look in this picture up here, which is an example of hydrogen bonding, we see this oxygen molecule of our oxygen atom, of water molecule number 1, has these lines between the hydrogen atom of our water molecule number 2, and that right there is the hydrogen bond. So that's the attraction again between the hydrogen atom here and the very electronegative oxygen atom here to create this hydrogen bond. Now it's important to remember, hydrogen bonds don't just exist between water molecules. All you need is your positively charged hydrogen atom and then any electronegative atom. Could be fluorine, could be chlorine, could be oxygen to create that hydrogen bond. In the case of water, this would be the resulting hydrogen bond here. So now let's look at the solubility of ionic compounds in water. So most ionic compounds are soluble in water. My example that I have for you is sodium chloride, table salt, dissolves in water. The positive end of the water molecule attracts the chloride ions, and the negative end attracts the sodium ions. Right? We know the opposites attract. That makes sense. So that means our chloride ions are going to be attracted to our hydrogen ions, and then our positive sodium ions are going to be attracted to our oxygen atoms in our water molecule. Okay? Excuse me. So, water molecules surround each other in the process of solubility, and this is called hydration. So essentially, if we think of our sodium chloride solution, we took our table salt, we dumped it in our water, we mix it up. As we mix it up, we disrupted the bonds and the interactions between the sodium ions and the chloride ions, so now those are floating independently in solution. But we know that it's dissolved, so the water has to be somewhere. Well, those water molecules surrounding either a chloride ion or surrounding a sodium ion, that's called hydration. So, when the attraction between ions in an ionic compound is larger than the attraction between the ions and dipoles in H2O, the compound will not dissolve. So when the bond is so strong that not even the dipoles of water can pull it apart, the compound is going to not dissolve into water. And it's important to remember that the chemical formula of an ionic compound in solution represents the overall composition of the solute. So an example is if we have NaCl aqueous, which we know from this AQ right here, that's all saying that the dissolved solute is made up of equal parts sodium and chloride. Okay, so we look at the chemical formula of an ionic compound in the solution to represent the overall composition of the solute. All right, so now we're going to move on to talking about molecular compounds in water. So we have dipole-dipole attraction that can occur between molecules of any polar compound. These forces are much weaker than the attraction between ions in an ionic compound, which we know. Those metals and nonmetals in an ionic compound are held together very strongly, whereas in molecular compounds, those dipole-dipole interactions are still strong enough to keep the molecule together, but they can be broken apart a little bit easier. However, these attractions are strong enough to hold polar molecules together as a solid crystal. Okay? So the strength does vary depending on what we're talking about. So if we're looking specifically at polar compounds in water, most polar compounds do dissolve into water. And we know that because the dipole-dipole attraction between solute molecules is much weaker than the hydrogen bonds, like we talked about in the last slide, that exist between the solute and the water molecules. Okay, so we have a bunch of sodium chloride floating around, we stir it up. The attraction between the water molecules surrounding it are so strong that they're going to pull apart that sodium and now have that hydration like we talked about, and those sodium chloride compounds not going to stay together. It's going to break apart because our hydrogen bonds are just too strong. But if we turn to look at nonpolar molecules, these ones do not dissolve in water, and that is because the attraction is too weak to break the hydrogen bonds. So now we're going to kind of turn our brains back to grade 10 science here, and when we talked about ionic compounds and molecular compounds for the first time, we definitely talked about their properties. And when we talked about their properties, conductivity was a big one. So we can use conductivity of aqueous solutions to test. So what can we test for? Well, conductivity tests can indicate if a compound dissolved in water is ionic or molecular. So you walk into the lab, you decide, oh, I'm gonna just explore, see what's around here. And all of a sudden you walk to the back and see a beaker filled with a solution. Don't know what it is, doesn't have a smell, so it's probably safe to assume, in this case it might be water because you might have saw someone using water. And you're like, I wonder if an ionic or a molecular compound was dissolved in here. Well, you can do a conductivity test and that will tell you your answer because solutions of ionic compound can conduct an electrical current, whereas molecular compounds cannot. Okay, so that's one way to test if you don't know if there's an ionic compound or a molecular compound in there. So now we're going to talk about predicting ionic solubility in water. So the first thing we're going to talk about is the force of attraction between two ions with opposite charges depend on two factors. So they depend on ion charge and ion size. So if we look at ion charge, the greater the charge on each ion, the less soluble the compound will be. So that means that an ion with +2 is going to be less soluble than an ion with a +1 charge. Then we're going to look at our second factor, which is ion size. And that just says that the larger the size of the ion, the more soluble it will be. So that's when we go back to our trends on our periodic table and use ion size to kind of gauge which element or which compound or which ion would be more soluble. And this is cut off here, but it's something you already know, so I'm not too worried about it. And it just says, use a solubility table to determine the solubility of ionic compounds in water. And we've done that before. You've done it, I've done it. You look at the compound you're given, you follow those solubility guidelines, and it will tell you if your compound is soluble or insoluble in water. So now we're going to predict molecular solubility in water. So this basically says, or our rule, is as the size of the nonpolar group in your molecule increases, the molecular compound becomes less soluble. So your textbook actually has a really great example. It's table 8.4, and it shows the arrow, which is the increasing size of the nonpolar portion of the molecule, moves this way. So if we have methanol, that's your CH3OH. That is soluble at 25 degrees Celsius and 100 kilopascals, which is a pressure reading. But we're going to focus just on temperature. If we move to ethanol, where we just add another CH group here, right? We can see the difference, still soluble. We move to propanol, which is another CH3 group, still soluble. But then we get to butanol, which has just one more CH3 group than propanol, and it's already less soluble. And then we move on to pentanol, another CH3 group, even less soluble than that. So as we can see, the size of the nonpolar group increases, the molecular compound becomes less soluble in water. That's all we have for today. Hope you enjoyed this lesson, and thanks for watching.